Hi everyone, welcome to Chapter 5. Chapter 5 is on standard scores, also known as standardized scores. And essentially what standard scores allow you to do is to, first and foremost, compare apples to oranges. Now, standard scores are used for other reasons, and we're going to get into that in this chapter. But let me just introduce the concept of standardized scores and comparing apples and oranges with an analogy that I think you can all relate to. So let's pretend that you are trying to decide where to go to graduate school. And you've got two offers. One university has offered you a $10,000 scholarship per year. And the other university has offered you a $20,000 scholarship per year. So again, one is, let's say, $10,000, the other's $20,000. So do you think you should automatically go for the $20,000 scholarship a year? Well, all things considered equal, right? Let's say they're both wonderful programs and great faculty and an area of the country that you would love to live in, etc. Before you decide on which scholarship to take, which university to go to, you probably want to ask yourself, well, how much is tuition? How much is tuition each year to begin with, right? Because although it might sound like $20,000 is the better deal, what if the annual tuition for this first university was $12,000 a year, and this one was $60,000 a year? Does $20,000 sound so great now? No, right? I would go for the $10,000. This is actually worth more when you consider that the annual tuition is only $12,000, all right? This one, the $20,000 scholarship, is actually worth less when you take into consideration that tuition is $60,000 a year, all right? So this would be an example of comparing apples and oranges, okay? Now, how are we going to do that in a fair way, in a way that makes sense? And that is, we are going to take our raw scores. These are scores that you've not done anything with. They're just the original scores that you collected. And if you're collecting raw scores from different distributions, like distribution A over here and distribution B, then when you convert each one to a standard score, what you're doing is you're putting all those scores on the same unit of measurement. They now belong to the same distribution so that you can compare them. All right, so we have two different distributions that we use most often for standard scores. And the first one is Z. Oh, I should say, or I should let you know, in Canada and Europe, we say Z, not Z. So when I say Z, then just know that I'm really saying Z. All right, or vice versa. If I say Z, Z, those words or letters are used interchangeably, the sounds, okay? All right, so the Z distribution then is a very common standardized distribution where we convert all scores to Z, and regardless of which distribution they came from, again, once they're all on the same Z distribution, we can compare them. And then the other standard distribution that is used most often is T, and the same thing. We can take raw scores from wherever, convert them to T's, and now we can compare them on the T distribution. All right, so let's look more closely at this concept. So a standard score or standardized score is a mathematically altered score which now belongs to a distribution with specific properties that allow for comparison between scores, among other things. All right, so it's been mathematically altered. So it's no longer a raw score if it's been mathematically altered. All right. Once you have mathematically altered that score, it belongs to a new distribution. We call it a standard distribution. And remember, it might be a Z distribution or a T. It depends, on, among other things, on sample size. And I'm not going to get into that just yet. All right. So you've altered the score mathematically. It belongs to a new distribution. That new distribution has a set of very specific properties, and it's because of those properties we can compare one score to the other, all right, to see which score really is best. All right. So, as I've said, the z-score is one specific type of standard score. You can take any raw score from any raw score distribution and convert it to a z-score. So any raw score in the universe and beyond, past, present, and future, any raw score can be standardized into a z-score. It can be converted. Now, you do have to have certain things in order to convert a raw score. All right, so in order to convert this raw score x into z, you need to know the mean of the distribution it came from. So if we're working with x, you need to know x bar, like what was the mean of the distribution? What was the standard deviation for that distribution? If you know these two things, then you can take this x and you can convert it to a z. All right. Now, this formula here works as long as your sample size is greater than 30. All right. And so we'll talk later about what happens if your sample size is less than 30. But as long as you have a decent sample size, again, take your raw score, subtract the mean of the distribution it came from, and divide by the standard deviation. And then you get Z. Pretty easy, right? Now, when you see a z-score, you know two things instantaneously. All right. The first thing you know, just by glancing at a z-score, you're going to be able to tell if the raw score that it originated from, whether that raw score was above the mean of its distribution or below the mean of its distribution. Now you might be asking, how can we know this at a glance? Well, look at the formula. All right, here's your raw score, here's the mean. All right, now keep in mind, standard deviation is always positive. You cannot have negative variability. Remember, standard deviation comes from variance, and variance is a squared number. So when you take the square root of a squared number, remember doing that? You take the square root of s squared to get s. S has to be positive, okay? You can have 0, you can have no variability, but you can't have negative variability. All right, so we know this is going to be a positive number. So when would z over here, when would that be negative? Well, it would be negative when this is negative, right? When our numerator here is negative. That will happen if your raw score is less than the mean. So if the mean was 10 and this was 5, 5 minus 10 is minus 5, right? So again, if your raw score is less than the mean, all right, below average, then that will give you a negative z-score. However, if your raw score is greater than the mean, above average, then when you subtract the mean, you get a positive answer. All right, so you see how that works? It's the numerator that determines whether z will be positive or negative. If you get a negative z-score, you know that the raw score that it originated from must have been below the mean, right? X had to have been below the mean. If you get a positive z-score, then that tells you that X must have been above the mean. All right, now that's the first thing you can see at a glance. Was the score below average or above average? And actually, you could know if it was average, right? What would the z-score be if this raw score was equal to the mean? What if you, let's say you took a test and you scored the mean, right? Well, if the mean is 85 and you minus 85, you get 0. So a z-score equal to 0, because 0 divided by s is 0. So if you get a z-score of 0, it means you're at the mean. Okay, so again, negative z-score means you're below the mean. Positive z-score means you're above the mean. And a 0 z-score means you are the mean. Okay, what's the second thing we can get at a glance? To be able to tell how far above or below the raw score is from the mean. And again, just at a glance. And how can we see this from the formula? All right. Well, we know if this subtraction here, if it gives you a negative answer or a positive answer, that tells you if you're above or below. But what about the actual size of the difference here? What if you are very, very close to the mean? If you're very, very close to the mean, this is going to be a small number, and that's going to make Z small. If you're very far away from the mean, all right, so if this difference here was large, then that means that you're going to get a larger Z-score. And that tells you you're further from the mean than if this was a small number. Okay, so again, to summarize, if Z is 0, it means you're right at the mean. If Z is a very small number, it means you're very, very close to the mean. And if Z is a large number, it means you're far from the mean. All right, and again, whether Z is positive or negative tells you if you're above or below. All right, so I actually like to talk about formulas and show you formulas when they help you to understand the concept.